Hey there, chemists. Welcome to our kind of culminating lesson here, all about redox chemistry. And today what we're going to be talking about is what is called a voltaic cell, but it really is basically a battery. So we're going to kind of talk about batteries. So before we can dig into batteries and kind of what batteries' purposes are, I want to talk really quickly about light bulbs and talking about the kind of lights that we have in our home. And I think with understanding kind of how that works, that will help us understand a little bit more how batteries are so useful. So if we think, how do I get my light to turn on and off? So in order to get our lights to turn on or off in our home, what we need to do is we need to essentially flip a switch. And what happens when I flip that switch? Electric current is going to flow through the light, right? It's going to flow through our light. And where do we get that electricity from? Well, we get it from different companies that provide us electricity. And so that electricity is provided by an alternate source. Okay? And one big thing that's key here is that we have the switch to flip this on and off. And why do we require the use of that switch? Well, we use the switch because that closes what is called a circuit, right? So our light will only work if the switch is flipped on or if our circuit is closed. If our circuit is open and we cannot have the electric current flow all the way through, then we are unable to have the electricity. And that's going to become really important for us when we start to talk about how the battery actually functions. So this leads me to, what is the purpose of a battery? Well, maybe you're kind of shaking your head and thinking this is a really silly question, this is really stupid, but I think that it's a great question, because why do we want to use a battery? Well, a battery is going to provide electricity, right, for our mobile appliances of sorts, right? So for example, I'm sure just like me, you guys all always have a phone nearby, and that battery in there is providing the electricity needed to power that phone. And what might we know about kind of batteries as they are? Well, batteries are going to store the energy for our use. And so what I want to look at today in this lesson is, how do batteries get their energy, or where do batteries get their energy from? And so to jumpstart us into this conversation, I want to take a look at two different reactions. Now, this is pretty much review. We've already kind of talked about the idea of spontaneity and single replacement reactions, but let's first go through and predict the products of our two chemical reactions provided here. In equation 1, we have copper metal looking to replace zinc metal. Now, again, this is copper trying to replace zinc because metal replaces metal. When we do this, we actually would get the products of CuSO4 plus Zn, okay? And this would be solid and this would be aqueous. Now, what about reaction 2? Well, in reaction 2, we're looking to have zinc metal replace copper metal. So we're going to end up with Zn solid, or I'm sorry, Cu solid. Let me erase that and rewrite that, okay? So we're going to end up with Cu solid plus Zn SO4 aqueous. And I want to know which of these two reactions will actually occur spontaneously. And if we need a reminder of what spontaneity is, spontaneously means without added energy, right? It's going to happen on its own. And so in order to do this, remember, to determine spontaneity, we want to use reference table J. Now, I don't have a PDF of table J pulled open, but each of you should take a look at table J and pause the video and really think about which of these is going to occur spontaneously. But for the purpose of kind of, going over things here and going quickly, I do want to mention that, or just go over it and tell you the answer, that the reaction 1 would have no reaction. Okay, so reaction number 2 is our reaction that occurs spontaneously. And so why does reaction 2 occur spontaneously? Well, according to reference table J, Zn is more active, right? And what does that active mean? It means that it's higher up on table J, okay? And so when the metal that is in its elemental form is higher on table J, it is able to replace the metal without any added energy from our compound. So zinc is higher than copper, and therefore the reaction occurs spontaneously. Now let's take a close look at our half reactions for equation 2. Again, we're going to focus on equation 2, eliminate equation 1 from the mind. Our reduction equation means, remember, reduction is a gain of electrons. And if something is being reduced, remember that means that our charge is decreasing over time. So assigning our oxidation numbers here, we have zinc is 0, copper is +2, sulfate is going to be our spectator ion, copper is 0, zinc is +2, and again, sulfate is our spectator ion. So of these two, which has the charge that's decreasing? That's going to be the copper 2+ ion. So Cu +2, okay, is going to become Cu solid. And again, this is aqueous copper becoming solid copper. Now, I haven't made a big deal about this just yet up until this point, but we actually do want to keep those phases around. So we do want to see aqueous versus solid in our half reactions at this point. And it's going to help us explain our battery a little bit better. Okay, our oxidation half reaction, okay, is going to be the Zn solid becomes Zn +2 aqueous. Now, last thing we have to do is add in our electrons. So we have copper 2+ ions that are gaining 2 electrons to become a copper atom. And for zinc, we have zinc atoms that are forming aqueous zinc ions by losing 2 electrons. So what's our net equation going to be for this reaction? For this reaction, our net equation is going to be Cu2+ plus Zn, okay? Remember, let's keep our charge aqueous and solid, forming Zn2+ aqueous and Cu solid. Now, because copper 2+ is gaining 2 electrons and zinc 2+ is losing 2 electrons, or zinc is losing 2 electrons, we actually did not have to multiply either. The number of electrons lost was equal to the number of electrons gained. Now, I want to know electrons flow from which species to which species. And you might be thinking, well, why is this really important? I want to take a moment to kind of pause and think about our discussion. We're talking about electricity today. And if you think back to the beginning of the year, how do we define electricity? What is electricity? As a reminder, electricity is the flow of charge. And note that electrons are charged particles. So when we're talking about electrons flowing from one species to the next, what we're really saying is our electrical current or our electricity is flowing from where to where. So looking back at our equation, note that copper 2+ is again gaining electrons, right? This is a gain of electrons, and our zinc is losing electrons. And so our flow of electrons is going to be from Zn to Cu2+. Okay, So the electrons flow from Zn, and again, solid, that's very important, to Cu2 plus aqueous. Now, we're going to dig in really into the battery on the next side of this notes sheet, but what I want to focus on really quickly, because this is going to help make redox reactions a little bit faster for you. Using table J in this term active that we said, what general rule can we then use about the species more likely to be oxidized? So again, just to review, zinc was above, right? Zn is above copper and is more active on table J, okay? And this is less active. And so which one of these species was oxidized? Again, the zinc was oxidized. So our more active is more likely to be oxidized in a reaction, and our less active is more likely to be reduced. So this should be a nice shortcut method now to double check if you're getting your oxidation reduction reactions correct. So more active equals more likely to be oxidized, and less active means less likely to be oxidized. I should not write it that way though, and let's call it instead more likely to be reduced. All right. So what I'm going to go ahead and do now is we're going to scroll to our next side of this notes sheet. It's going to look overwhelming. There is a lot of stuff to cover here. You know what, actually, no, let's not do it this way. Let's actually pause here. We're going to take what we learned today and we're going to use this in practice in class tomorrow. And then tomorrow, we're going to finish up this notes sheet and learn all about how the battery setup actually works. So sorry to leave you guys on a cliffhanger here, but we're going to go ahead and pause. Have a wonderful rest of your day, and I will see you guys tomorrow.